I will just formally introduce the speaker before the session starts. Sri Manash Bagchi is a senior curator at Vishweshwariya Industrial and Technological Museum, Bangalore. He was previously in Regional Science Center and Planetarium, Calicut. Both these centers, and there are other 28 centers also, together are coming under National Council of Science Museum and Autonomous Scientific Organization and the Ministry of Culture, Government of India. So, besides working towards technology development for the museum, Manas has curated several tropical galleries, including gallery on cosmology and astronomy. Further, he has curated exhibition and galleries on space science and astronomy, nuclear power, oil and natural gas, genomics, water, etc. Before his current assignment, he was also the head of the computer division of Central Research and Training Laboratory under for the research and development, which is the research and development wing of National Council of Science Museum. He has developed several technologies: 3D stereoscopic video editing and playing, automated stop motion animation development system, seamless visual seeker, etc. Besides technology development for the museums, he has taken keen interest in social ramification of various science and technology innovations. He has contributed as an editor to the science supplements of the Indian daily The Telegraph and Ajkal, published from Kolkata. He has published a number of papers and he has a number of patents to his credit. So we have a very eminent speaker, and it's your turn. Present your talk.
Thank you very much, and thank you for this rather elaborate introduction. I'm always one of Regional Science Center Calicut, and I still remain the same. So anyway, it's a great opportunity to talk to all of you. And Dr. Sule has already presented at data level some of the issues that are of concern for us as well. So let us get into it, and I'll just share my presentation and start talking. Just allow me some time.
It's visible. It's okay.
It's on now?
Yeah, it's fine.
Okay. So my brief is to talk about cosmology in an hour, and you can understand how it would be like packing the whole universe in an hour. So I thought that let us call this session Universe in an Hour. So naturally you can understand that the elaboration is not possible. I will try to give you an impression what we know about it and how we know about it, what are the current challenges. A little bit of it Dr. Sule has already very nicely discussed. I will try to elaborate upon, and based upon that I'll try to sew up a few more ideas. Well, a very interesting challenge in cosmology is that what Shakespeare once explained, Shakespeare once stated in Hamlet, and Hamlet said that I could live in a walnut shell and feel like the king of the universe. We human beings are almost like that. Even though we have never gone anywhere beyond the moon, we still can think of and we still can create these structures that are much beyond our galaxy and even far off towards the edge of the universe, if there is any. We'll try to analyze what it is and how it is exactly like. Okay, so the agenda is to understand cosmology, which is the study of the origin of few things. What are they? Current state and future of our universe. And now this field has been revolutionized by many discoveries during the last century. We will try to cover a few of them in a nutshell, because you understand that packing the universe in an hour is a very, very difficult job. So let us get into it. First, the observations of global properties, which takes us to this understanding of cosmology. Now, until a few hundred years ago, uh, the solar system and the universe were equivalent in the minds of scientists. A very interesting observation is that even when Einstein proposed his general theory of relativity, there was no idea that actually there are multiple galaxies in this world. Einstein still knew about a single galaxy, but a few centuries before that, we actually considered that the solar system is the whole world and there's nothing beyond that. So that was the concept, and in that edifice, many ideas of science were created. But then the discovery that the Earth is not at the center of the solar system was a very important step in the development of cosmology. Early in the 20th century, when Shapley established that the solar system is far from the center of the Milky Way even. So first the Earth was shunted out of the center of the galaxy, center of the solar system, and then the solar system itself was also shunted out of the central position of the galaxy. And so by 1920, the stage was almost set for a critical observational discoveries that led to the Big Bang model of the universe, which was coming up. And once everything was, everything were from, we are in a vantage position. When those things were shifted out of the central position, we could be bothered about the structure, the superstructure. Then what else? If we are not at the center, then what this structure is like. So Earth displaced was an important issue. Now, Dr. Sule just described about the Hubble's law, but there is something interesting in the Hubble's law itself. In 1928-9, Hubble published the claim that the radial velocities of galaxies are proportional to their distance. The redshift of galaxy is a measure of its radial velocity, and that can be measured using spectrograph to determine the Doppler shift. Now, this is the plot that you see on your screen. Dr. Sule used a later refined plot, but this is the plot that Hubble had in 1929. This is his data. And if we look at his data, we can find out certain things. The slope of the fitted line here, it comes as 464 kilometer per second per megaparsec. And it is now known as the parameter that we are talking about. The value is different, of course, but the parameter that we are talking about, we call this H0, and this is the Hubble's constant, which Dr. Sule was also talking, that this is the proportionality constant, and that comes in Hubble's equation. Now, since both kilometers and megaparsecs, 1 megaparsec, you all know, that is about 3.086 into 10 to the power 24 centimeter. Since they are both units of distances, the simplified units of H0 are actually 1 by time, and the conversion is given by the equation that I have used here. It is shown on my cursor, 1 by H0, and that is 978 gig year. Gig year is 10 to the power 9 years. And when that thing divided by H0 in kilometer per second per megaparsec. Now, what is in that? What is the interpretation? I told you that thus Hubble's value is actually equivalent approximately to 2 gig year. Now, since this should be close to the age of the universe, that is another interpretation in this session. Actually, since we have only 1 hour time, so I will take a lot of results in. We have to take that as established results. I will try to point out when it is not established or when there is some dispute in it. But more or less, these are derivations and established results that sometimes we will use, and I will tell them. So since this actually is interpreted and it should be close to the age of the universe, and we know it was also known as 1929. one thing I have tried in this session is that since I saw that in this course you were requesting about the presentation itself, so I tried to more or less give a course structure in the presentation itself, that so that even afterwards, if you read them, then you'll know what the story was all about. And it was known, that is why I have written that even in 1929, that the age of the Earth is at least larger than 2 billion years. So Hubble's value for H naught led to a considerable skepticism about the cosmological models, whether it is true, whether it is correct, because we knew that this model was not giving us the actual age of the universe. It came much smaller than that. So it also motivated alternative ideas, and the steady state model came up, which now we never consider at all. So this was the interpretation of Hubble's data, and cosmology was being formed. And what was the confusion? The confusion was lateral work found that Hubble confused two different kinds of Cepheid variables. The stars that are used to calibrate distance, you already know that by the distance ladder discussed by Dr. Sule. And also that what Hubble thought were bright stars, in some places he called them bright stars, and accordingly he tried to measure something. He thought that those are bright stars in distant galaxies. They were actually not outside the galaxies, and they were actually what is called the H2 regions, which are regions of interstellar atomic hydrogen, and that is already ionized. So he misinterpreted the thing, and that is why some error crept into his data. So as a consequence, what happened? The consequence was correcting for these errors has led to a lowering of the value of the Hubble constant. So HST distance scale, and now as Dr. Sule also pointed out, there are two accepted values now. Accepted values in the sense, I mean, actually if it has to be accepted value, then it should be unique, but it is not that. But now what is considered, that two very standard values are talked about. We still do not know whether they will converge at some other value, or there is a dispute that will still continue, or it will require some other interpretation. But whatever the situation is, there are two values that we talk about now, and one is the HST distance scale key project team. It is a project that tries to measure the Hubble constant. Later on, you probably may contact Mr. Ganguly, because once we tried to give a comprehensive story of the Hubble constant, what is it and how it is measured. I think he has got the text with him, which he may share with you. And what this team, they calculated the value to 72 plus minus 8 kilometer per sec per megaparsec. While the other team, it's called the Sandage team, they got it 57 plus minus 4 kilometer per sec per megaparsec. So you can understand that there is a considerable difference in these two values. So there's an alternative thought that there are other alternative methods. If they can be developed, we can probably sort out the discrepancies or the differences in these values. That is an idea that prevails at the cutting edge level. So other methods to determine the distance scale that are included is the time delay in gravitational lenses and what is called the Saniev-Zeldovich effect in distant clusters. So both are independent of the Cepheid calibration, and that is why they sometimes are thought to be a way out which can settle down the issue. That is how it is thought, because other two methods are dependent upon Cepheid calibration. And very interestingly, the alternative method that determines this value at 65 plus minus 8 kilometer per second per megaparsec. So it is somewhat in between the other two values. Now there can be a physics interpretation of it perhaps. Did it change? Did it change it different ranges in different scale factors? Those are much more detailed questions that we do not have the scope to discuss immediately. What we would like to go to is this, that these results are consistent with a combination of results from CMB anisotropy, CMB or CMBR, as you know it, Dr. Sule has already explained, and the accelerating expansion of the universe that gives 71 plus minus 3.5 value for the same parameter. And with this value of h naught, the age comes to 14 gig year, while the actual age that is determined from other methods, we accept it as 13.7 plus minus 0.2 gig year. So the problem here is, while going to settle down the age of this universe, we have several methods, and in that distance measurement, the velocity measurements, the spectrographic use of, the spectrographic analysis of the light that comes from distant galaxies, those become very, very important. There are many more experimental issues in it, and there are some theoretical predictions also. We could not settle down all the issues altogether. So now we understand that Hubble's data in 1929 is actually quite poor. Why so? It is because individual galaxies have peculiar velocities of several hundreds kilometers per second, and Hubble's data only went out up to 1200 kilometers per second. He did not take more than that. But the data shown here now, this one Dr. Sule mentioned, this is a refined data. That data is from type 1A SME from Rice Press and Krishner in 1996. This was published, and this extends up to a speed of 30,000 kilometers per second, and provide a dramatic confirmation of the Hubble's law. If you remember the previous image, you will find out that the points were quite scattered here and there. But in these, the fitting of the curve is fairly accurate, and it indeed appears like that proportionality curve, which you can present as the equation given here, that the velocity, which is actually the rate of change of distance with the time, and that is proportional to some constant multiplied by the distance itself. So it is proportional to the velocity of a galaxy, is radial velocity is proportional to the distance of the galaxy itself. There is another part of it. The fitted line in this graph, once again we can calculate the slope, and this slope can be calculated as 64 kilometer per second per megaparsec. Since you measure the radial velocity using the Doppler shift, it is often called the red shift that you have already seen. The red shift of z is defined as 1 plus z is equal to lambda, with lambda by lambda observed by lambda emitted, where lambda is the wavelength of a line or feature in this spectrum of an object. And that change happens because the linear distance redshift law that was found by Hubble is compatible with a Copernican view of the universe, that our position is not a special one. And first, we have to note that the recession velocity is symmetric. This is interesting. If you look at the two galaxies here, then you can find out that if A sees B receding, then B also sees the A receding, as shown here in this diagram. And the lambda observed by lambda emitted is the ratio through which we give this redshift that we have already mentioned. So you can understand this thing, how it is done. Now, to present such things, we use a tool called a space-time diagram. And what is a space-time diagram? If you look at the image that is there on our screen, let me explain a little bit. What we can see here is that when we can, what we can see and when we can see in the universe is important. Why it is? It is because we have to understand that seeing itself involves a lot of physics in it. A good way to keep track of these concepts is done through the space-time diagram. A space-time diagram is just a graph showing the position of objects as a function of time, but there are certain methods followed in it. The usual convention is that the time is put up in the vertical axis, and the bottom is henceforth the past or early times, and the top is the future or later times. And the point of this graph describes both a position and the time, so we can call it an event. All these points on this graph are really events, and this particular graph, I'll tell you that this particular graph we are seeing here, it actually shows the motion of the earth around the sun, and if we plot it in such a space-time graph, it will appear like this, right? Now, the slope of the and one more thing that we have to know, that these lines, those which appear in such graphs, we call them the world line, right? So the slope of the world line for a particle, it shows its velocity in the reference frame of the diagram. The space-time diagram that was shown there, and here you can see that it shows particles with different velocities, which has got different velocities. Those values are given there. So this is how they are presented. And there is one more improvement of the space-time diagram as we place it, because the speed of light is very special in relativity. That is why the special relativity was formed altogether. It is the ultimate speed that we talk about. The space-time diagrams are often drawn in units of seconds and light seconds. That is in a form where in a light second, in a second the light moves a light second. So similarly, if we use such kind of units, then we can show that a unit slope is given to these lines. 45-degree angle corresponds to this speed of light, and the set of all light speed world lines going through an event defines the light cone of that event. The past light cone is the lower part here, lower part of the image. Anything that happens in the past, those events have to be here, and anything that happens in future will be there in the upper light cone. And the fancy light picture of this actually shows both the past and future light cones of an event where the two world lines cross. While the schematic version of the right is easy to use, there is more complicated. More complicated diagrams are formed out of it. Here, why I presented is this, that if you look in this diagram, which actually presents the situation from two different galaxies, how these world lines will appear. This is a confirmation that the Hubble's law is true, because when we plot such kind of space-time diagrams, we can see that if we do not follow the linear relation, and if we consider that the quadratic relation is there in Hubble's equation, then what will happen is you will see that when the world is expanding, the universe is expanding, there will be distortions in the elements which are under this expansion. But that is not observed. The shapes are more or less preserved, and that can happen only if the linearity of this equation is followed. So we more or less know that the Hubble's equation is remarkably true, and that defines the condition the dynamics of the universe, how it is going, how it is evolving. The Hubble's law actually defines a very special frame of reference at any point in the universe. An observer with a Large motion with respect to the Hubble flow would measure blue shift in front and large red shifts behind. Instead of the same red shifts proportional to the distance in all directions, and this will create the distortion. Thus, we can measure our motion relative to the Hubble flow, which is also our motion relative to observable universe. A co-moving observer will be at rest in this special frame of reference. So our solar system is not quite co-moving, and we have a velocity of about 370 kilometers per second relative to the observable universe. The local group of galaxies, which include the Milky Way, they appear to be moving at 600 kilometers per second relative to the observable universe. And as a result, as a result of the linearity of the Hubble's equation, what happens is presented here. If you look at these two images, you can find out that there can be structures formed of the elements in which there can be two structures, and there is some peculiarity in it that I'll mention. That in one case it may be isotropic, but it may not be homogeneous, the distribution of the galaxies or the distribution of the elements in such patterns. And in the other case, it may be isotropic, one isotropic but not homogeneous, and in the other case, it is homogeneous but not isotropic. Let us see how it is. Now, Hubble measured the number of galaxies in different directions at different brightness in the sky. He found that approximately the same number of faint galaxies in all directions exist. And even though there is a large excess of bright galaxies in the northern part of the sky, still more or less there is a uniformity. So when a distribution is same in all directions, we call it isotropic. And Hubble, when he looked at the F/4 brighter galaxies, he saw approximately 8 times more galaxies than he counted, which were brighter than F. So since flux is 4 times smaller implies a double distance, and hence a detection volume that is 8 times larger, this indicated that the universe is close to homogeneous, having uniform density on large scales. Now this large scale thing is important. So this figure, what you are seeing on your screen, here you can find out that the figure above shows homogeneous but not isotropic. This is homogeneous but not isotropic. But the second one, it is isotropic but not homogeneous. So such conditions may occur, but I'll do that. The point is, we know that high density things like Earth exist in this universe. So exactly at any point we cannot call that the Earth is homogeneous and isotropic. Like this image that we are seeing here on the screen, it is a simulated image, but this simulated image still shows the distribution of the galaxies, and we can see, if we look at the large scale, then we can find out that it is more or less smooth distribution all over. In terms of data, we can see it even better. And here is this data from the Peacock and Dodds, this graph. Now here you can find that this is not uniform in this region, but once you go beyond the 100 megaparsec, then the uniformity is quite noticeable, right? And what do we say? We say that for 100 megaparsec regions, the universe is smooth to within several percent. Redshift surveys of very large regions confirm this tendency towards smoothness on the largest scales. And even though nearby galaxies show large inhomogeneities like we have in Virgo cluster, the supergalactic plane, in the supergalactic plane, but over the long distance of 100 megaparsec or so, at that scale, the distribution more or less appear to be smooth. So the case for an isotropic and homogeneous universe actually became stronger after the Penzias-Wilson discovery of the cosmic microwave background. It happened in 1965, and they observed that an excess flux of 7.35 centimeter wavelength, equivalent to the radiation from a black body with a temperature of 3.5 degrees Kelvin, are coming from all directions. And many groups have since henceforth measured the intensity of the CMB at different wavelengths, and currently the best information data is from the FIRAS instrument, which is from the COPE satellite, and let us see what does it show. This is the curve that we got from the FIRAS, and the x-axis variable is the wave number, or 1 by wavelength in centimeter, and the y-axis variable is the power here, and the power per unit area, per unit frequency, per unit solid angle, and this is measured in a unit called megazansky. Now, a Zansky is 10 to the power minus 26 watt per square meter per hertz. Now, the error bars here are shown, they are amplified by 400 times to make it more proper. And with this, now we more or less confirm that the value of the radiation temperature is 2.725 Kelvin. The funny thing is, what Dr. Sule also mentioned, that more or less the temperature of the CMB is almost same all over the sky. And this figure is an interesting map where wherever the temperature is 0K, that is shown as black, and wherever it is 3K, it is white, and you will find that it is almost smooth. There is hardly any variation in the CMB, and that generates some more questions. Thus, what happens is the microwave sky is extremely isotropic, that you can see. So these observations are combined into the ultimate cosmological principle that we now accept, that the universe is homogeneous and isotropic, and we conclude that based on such type of observations, and this supports the Big Bang. Why this Big Bang support? The piece of evidence for Big Bang is in the abundance of these light elements, like hydrogen, deuterium, and helium, and lithium. Uh, we conclude this way, that as the universe expands, the photons of the cosmic microwave background, they lose energy due to the redshift, and CMB becomes cooler and cooler. And that means, in fact, we are very fortunate that we are at a period when we are still being able to measure CMB. If it becomes even cooler at one point of time, we will not be able to measure it with that accuracy. So that means the CMB temperature was higher in the past. And when the universe was only a few minutes old, the temperature was high enough to make the light elements by nuclear fusion. The theory of Big Bang nucleosynthesis thus predicts that about 1/4 of mass of the universe should be helium, and experimental measurements are close to it. So that we take as another proof that Big Bang was really true. So this far about the anisotropy and isotropy and homogeneity. There is another characteristic of the universe that we discuss and that we are concerned about quite elaborately, and that is called spatial curvature. Now, it is a consequence of the general relativity. That is another result that we take in here, is that the curvature of space actually depends on the ratio of the density of the space. We call it rho and rho critical. So this we represent with omega, and we give it this value of the ratio of rho and rho critical. And what is that? Now, critical density, what do we mean by critical density? The critical density is the density of the universe, which is necessary so that the expansion of the universe is just barely sufficient to prevent a recollapse. It will not recollapse, it will not be pulled back, everything will not be pulled back into a big crunch once again. Now, if you want to calculate the numerical value of this critical density, that becomes a mumbo jumbo like this. It's quite elaborate, and without relativity you can't calculate that. That is another particular thing, that understanding cosmology without getting into the details of relativity is a difficult proposition. But still later on it was found that even though results are all derived from general relativity, general theory of relativity, still applying not that difficult mathematics, applying algebraical mathematics also, results of cosmology are quite accessible. So what we now know is that if the value of omega is less than 1, then the universe has a negatively curved or a hyperbolic geometry. And if it is 1, then the universe has Euclidean or flat geometry. But if the omega is greater than 1, then the universe has a positively curved or spherical geometry. Einstein initially felt that it would be a spherical geometry. Now, the zero density case has a hyperbolic geometry, and since the cosmic time slices in the special relativity coordinates, they were hyperboloids in this model, right? So what is the current result? Einstein told us in his theory of general relativity that on small scales the space would be dimpled by massive objects such as stars. So wherever we find massive objects like stars, galaxies or clusters, there the space-time will be curved. And on large scale, however, where the assumptions of homogeneity and isotropy still applies, their space must have same average curvature everywhere. Okay, so consider this can be considered as an analogy. It is like an ant. Our position is like an ant which is wandering over the surface of an orange. The ant will encounter small dimples, local dimples here and there. But if the ant wanders far enough, it will still discover that the orange is spherical or average. And on large scale, there are three possibilities of the average curvature of this space. The first possibility is flat space. The two-dimensional analog of the flat space is a plane, and in this, if we create a triangle in this space, then we will find that the total sum of the vertices at the triangle, angles at the vertices, they will come up as 180 degree. But if it is not so, and if it is spherical, then in that case it will be more than 180 degree, and if it is less than that, then it will be less than the triangle angle. Some of the angles at the vertices of the triangle should come as less than 180 degree. So we can very easily say it is easily measurable, but it is not. There are methods which are applied to understand whether we can really determine it or not. And the most promising technique for determining this curvature involves looking at the angular size of very distant objects, because the light is coming from them, and we try to determine what sort of curvature they take. And for that, we try to identify hotspots in the cosmic microwave background. And in flat space, the light from these hotspots must travel along the straight line, or in positive curved spaces, they will come in bulge and converging lines. And this has the effect of making the hotspots look larger, and then they would be in flat space. Conversely, in a negatively curved space, the hotspots would look smaller. So we need to determine it, but they are so small, and experimental techniques are so very difficult. It is difficult to say conclusively what it is. And along with that, even though before we jump into something else, let me comment that more or less the conclusion is that the geometry of this space is flat, but that is a surprising thing. There are reasons for that, why it is still an open question, and we will go into that as well. As it turns out that the actual size of hotspots, which is about 1 degree across, is just what cosmologists would have expected in a flat universe, what we measure. More or less, that is what we see. It indicates that it probably is a flat universe. But precise measurements lead cosmologists to conclude that the universe is flat, though, and has an infinite volume. That is more or less the consensus. But we can't rule out the possibility that it has a tiny amount of positive curvature as well. And in that case, the universe would be finite. The volume of the universe would be finite. Although it would be very, very large, definitely, but still we cannot absolutely rule out that possibility. So it's an open question there. And I'll suggest a reference if you want to go further into it, then with this reference you can go into it. And when we model it in such a way, there are additional problems. If you look at this image, you can find out that we are considering two spaces here. Now, suppose we say that the universe has expanded over last 13.7 or 8 billion years, because it is 13.7 or 8 billion years old. And here we are considering two regions, one this region and one this region, which probably say are 10 billion light years from our place. Now, this one is 10 billion light years and this one is 10 billion light years on two different directions of the sky. So there would be about 20 billion light years distance between them. The question is, even though light can come from their end to our place, from both of them, actually light cannot go from one to the other. So what happens as a result is we can see regions in this universe which have not yet communicated among themselves. So each of them is confined within their particle horizons. They are called particle horizons. So the cosmic microwave background radiation that is coming to us, even though with the help of that we can identify those distant places which are 10 billion light years away, we do not have any clue how, without communicating between themselves, without exchanging any energy between themselves, how they are coming to a similar equilibrium. Actually, they should have been different. More expectation is they should have been different, but we do not know how it happened really. There are propositions, there are theories that has been proposed to understand how it can be, and it is called inflation theory, but there are skeptics about the inflation theory as well. So this is the particle horizon problem that bugs us still. And here we explain that in accepted relativistic physical theories, no information can travel faster than the speed of light. In this context, actually, information means any sort of physical interaction happening through exchange of photon or anything between two regions. So the two galaxies in question cannot have shared any sort of information. They are not in causal contact. In the absence of common initial conditions, one would then expect that their physical properties would be different, as I told, and more generally, the universe as a whole would have many more varying properties in causally disconnected regions. But the CMB is so smooth everywhere that becomes a query and an open question how it still can happen. And that is why this horizon problem that I have described, it has happened. We have calculated that if two galaxies, they remain separated by more than 2 degrees, they will actually lie outside one another's particle horizons. So they are supposed to be different, but even beyond this level, we are finding that the smoothness is quite well established. So we know that we know for, I mean, we need further theories about it. And the flatness problem is also a problem and an open question. It is because to have the flatness, we know the critical the density of the universe has to be very, very close to the critical density. Even though measurements show that it is the fact, it is almost the fact, but we cannot be sure, and we are not sure. It's a huge chance. How can it be exactly close to the flatness? The critical density that is required for flatness. How is that possible? It is such a chance that scientists are still not confident that that should be the case. So they are trying to find out what could be the reason for it. And what is being proposed as a reason is the inflationary scenario, and it is a modification of the Big Bang model in which it's said it's a large cosmological constant exists temporarily early in the history of the Big Bang, it is said, and it leads to a rapid acceleration, accelerated expansion of the universe, which is then followed by normal Big Bang expansion. So this early rapid expansion is infused into the Big Bang model by this inflation theory, and this helps to explain the case. The two problems that we dealt, they are explained, and this was proposed by Stravinsky and Guth, and how they can deal with the problem, let us explain that. The flatness in case of flatness problem, it says that imagine living on the surface of a soccer ball. It might be obvious to us that this surface has a curvature, but yet if it expands at a very, very high rate, it may expand to a very big level where the curvature at three-dimensional universe will reach to near flatness. So that very early and huge inflation may cause the flatness to come into the universal structural geometry. That is one proposal, but still there are other problems, and at the same time it is also said for the horizon problem that since inflation supposes a burst of exponential expansion in the early universe, it follows that distant regions were actually much closer together prior to inflation than they would have been with only standard Big Bang expansion. Thus, each region could have been in causal contact prior to inflation. So now we are saying that at current condition, they were never in contact. But if the contacts have happened even earlier, before the before the standard Big Bang expansions set in, then probably this could have resulted in this flatness and solution of the horizon problem. So more or less, this is the condition now. There are many more open questions. There are many more criticalities and details that we can get into, but that is more or less what we can do in an hour. So I will refer to all of you that if there are still unanswered questions, you can send them to my email, manush@work@gmail.com. It is on your screen. And if you are interested in further details, I'll suggest a very rudimentary level book, but I like this book because the presentation of it is very logical and it is quite picturesque. So this book is called How the Universe Works, Introduction to Modern Cosmology, and it is by Sergei Parnovsky and Alexei Tarnovsky. Uh, you can get this book very easily. It's a small book. It's not a very detailed book, not very, very mathematical. And the fun is, even without going into the tensor analysis and the actual mathematics of general theory of relativity, this book deals with algebraical forms of the results. Okay, so I think I've consumed my time and I'll stop now. Thank you very much.
Thank you very much, sir, for your valuable talk. And I hope all of you have enjoyed the talk and you saw a overview. As he has already said that cosmology is a typical mathematical and very specialized subject, but to get a glimpse of it, what is the subject all about and what are the various um, problems which are dealt with it, part of it was put up before all of you. Now if you have any questions directly, for just few minutes are left, you can directly ask the speaker here itself. Otherwise you can ask it afterwards also, as he has given you the email. But now if somebody wants to ask anything or give a comment or say some suggestions, you can either directly ask by unmuting yourself or put it in the chat box. Anybody?
Can I ask a question?
Yeah, yeah.
Yeah, so hello sir, how are you? It was a nice talk. So my question is like, there is a concept that universe is expanding and there is a finite time is needed if from the end of the universe, like observable universe, it has to reach to us. So in that way, we are like getting into a universe which is becoming smaller and smaller. So can you elaborate little on that? Like,
No, I didn't get the question actually. What is
yeah, so
happening?
yeah, so universe is expanding, right?
Right.
And lightness, and it's also accelerating. The expansion rate is also accelerating. Yeah. Now there is a observable universe till which we can observe, depending on like how far you are and light can reach. Now the concept is that region also becoming smaller and smaller in space due to the fact because the at the very end is also going out of the observable universe. So yeah, so
It is true, but I'm not much aware of it.
okay, yeah.
I do
So
not have any technical study in that
yeah,
region.
yeah,
I
yeah.
refrain myself from commenting it.
No, I was also not very had a technical details of cosmology. Just I also came across the idea. So yeah,
I have not studied in that region, so as of
yeah,
now, I will reserve my
yeah,
comments
yeah. Yeah, maybe
until
later
and
on you
unless
can
I study it a
discuss.
little
Yeah,
better.
yeah, yeah. It just looks to me like very interesting, but I also personally could not find to read further and on it. Yeah. Sometime maybe I will and
We'll
also
get
will
into it.
discuss.
We'll get into it.
Yeah, sure, sir. And it was nice talk. Thank you, sir.
Thank you. Thank you.
Any other questions or comments? Okay, so if there are no more questions, I think I will thank the speaker once again. So he has taken his time and he has come here and delivered his talk. So thank you, sir, once again. And we conclude this
Thank
session.
you. Thank
And
you.
yeah, and we break for lunch now. And again, we will meet at 2:30 sharp for the final session of today's. Thank you. Thank you.